All right, how's it going, everybody? Hope everyone's staying nice and cool. So I'm going to talk today. My talk is Beyond Metrics and Traces using the continuous profiler for low-level optimization. Like she said, I'm a senior staff engineer at Braze, been there for quite a few years, and often focus on a lot of performance problems across a lot of different teams. So the continuous profiler has been an immense help to us in identifying those. So today we'll go over a couple of them. So I've got a couple examples. One is a dynamic class memory leak that we'll go over, talk about how what the original problem we were facing was and how we ended up figuring out what it even was. We'll talk about excess allocations from the dup method. So Ruby, that's kind of the shallow clone of an object. So a lot of similar things in other languages. We'll talk about app observability tools and how I kind of imagine profiles to fit into the other tools that you may be used to using. And last, we'll follow up with some things that we're excited about at Braze, things related to the continuous profiler, either using it in other places or other additions that we hope to see in the future. So a quote from Braze engineers: "We need to find a way to look at what objects are still in memory." This is a frequent quote from us for years and years. We have a monolithic platform code base built in Ruby. And if anybody has ever written some large application, especially web application, in Ruby or another dynamic language, you'll notice that memory has this fun attribute where it kind of grows and grows and grows, almost logarithmically, sort of plateaus, but it can always keep growing. And so oftentimes, if you have a large code base, that means that the amount of memory that your code needs to run gets bigger and bigger, and that can cause all sorts of problems. So before we get into it, what does Braze's platform actually do? So Braze is a software as a service platform. It's built to allow brands to create relevant, memorable experiences that support stronger consumer and brand relationships. So the way that we do that, it's marketing automation software. Our customers log in. They create all kinds of campaigns, all these workflows we call canvases that are sending their users messages. So we have all kinds of customers. In fact, 2,000 plus customers at this point. I think it's even 2,100 plus now since I started doing these slides. And we send billions and billions of messages a day on all kinds of channels all over the globe. Our customers' users constitutes well over 6.2 billion users. So when you are looking at performance problems, something that you think is very small and insignificant at that scale actually translates into thousands, tens of thousands, or even hundreds of thousands of dollars. So very important to pay attention to the little stuff. Some things that we send, so just a real quick idea, just so you know what I'm talking about. We send mobile push, in-app messages, something called content cards, which are, if you think of an inbox or something in an application, iOS live activities. We also send email, SMS, kind of all the things that you think about if you've ever used marketing automation software. So lots of fun things, all kinds of features, with all kinds of places for things to go wrong, which is always fun. So a 50,000-foot view, just to have an idea. So I said we have a Ruby monolithic platform. We have some microservices for other purposes, but a lot of the content for this talk is going to be about the Ruby platform monolith. So it's kind of deployed in 3 different ways. So we use Rails and we use Sidekick. So our dashboard, all of the AJAX calls, all the backend sort of data for all of that is served with a Rails application, all as part of the same code base. We have APIs, so both what we call our SDK API, which is where our SDK, which lives on our customers' applications, is going to be sending data, pages people open, events that people do, purchases people make, to us for us to ingest that data and potentially trigger messages or update profiles, things like that. But the real meat of the application is going to be this thing called Sidekick. So has anybody ever used Sidekick or heard of Sidekick before? A couple of the Braze folks in the front for sure, a few people in the back. Awesome. So if you've not heard of it, you may have heard of Celery. Celery is another asynchronous job processing library in Python. Sidekick is sort of the de facto one that you'd use in the Ruby world. So it's used by a lot of folks. I believe GitHub uses it. I'm pretty sure GitLab uses it. Shopify for sure uses it. Any large Ruby shop is probably pretty familiar with it. And so all these things talk to our databases. We get data in from the outside world via the dashboard and the APIs. And we have a product that uses Kafka called Currents that will push that data to the outside world. But just for an idea of how it all fits together, I figured I'd give you the 50,000-foot view. And onto the examples. So I said first we'd talk about this dynamic class memory leaks. This is a problem where that nice logarithmic curve I described it was not actually quite so logarithmic. It was actually, in fact, much more linear than logarithmic, which you can imagine causes all kinds of problems. So the initial problem, we use Kubernetes to manage applications. That's not actually the problem, just some setup. Some people might disagree with me there, but our platform pods have this habit of linear memory growth as they age, right? After a few minutes, you'll see it at 500 megabytes. After a few more minutes, it's 700 megabytes. And it wasn't having that nice sort of logarithmic plateau that we want to see. So they kind of do this naturally. This just happens. But like I said, ours is growing suspiciously fast. And with Kubernetes, this is a common pattern that people have for dynamic languages like this in Kubernetes is you use some tool, I think it's called pre-killer. And what it does is it understands the resources that you have configured with your deployments, where you say, only allow it to use this much RAM, only allow it to use this much CPU. And once the allocated memory starts to hit a certain point, you just sort of warn your application and say, hey, I'm about to turn you off, but this is just a signal before I hard turn off the switch. You should probably do some cleanup before you're shut down. And we saw that that was happening pretty frequently. So if we look at this screenshot from Datadog logs, I've got a nice little search there for the phrase too large at. We can see this lovely graph where this is happening thousands and thousands of times, way more often than we want it to happen. And what we want to do is we want to figure out what's causing it. So we know that this is sidekick workers, this particular thing that we're looking at, and it's growing in memory in a way that we don't want. And one of the metrics that we look at is called the recovered jobs metric, and this is a built-in part of Sidekick. We run something a little bit differently internally than this, but this is straight from their documentation. They basically, as workers are running jobs, they move it to a private queue, and a background monitor process looks at that private queue, and if the same job has sat there for a long time, we just kind of assume after a certain amount of time, that worker must have failed. Let's go ahead and take that job, put it back into a queue to get worked on, and we'll increment this counter for recovered jobs. And we saw that counter get a little bit higher than we wanted to see it. So here's where we used metrics, where we're looking at the number of recovered jobs, and we're looking at a few specific ones here, but it was kind of all over the place. And we tried to apply this thing that I've been calling frequency analysis. I don't know if this has a really great term. But what we want to do is we want to look at all of the recovered jobs, but divide it by the frequency by which we do each of those jobs. Because the way Sidekick and Celery and other frameworks like this work is that workers aren't just doing one type of task. A single worker might have 100 different kinds of jobs that it runs, just depending on whatever it picks up from the queue. So it's not always very evident which job might actually be causing your out-of-memory error. So you have to do some tricks to figure it out. But Sidekick uses multiple threads. So if your process gets killed, you've got 4 different options for what might have caused it to die. So that really muddies up your data, and it makes it very difficult to understand, which, unless it's something absolutely egregious, which one of your jobs is the one that has the problem that you should investigate. So here's where the profiler comes in. So we turned on the continuous profiler. We turned on all of the alpha and beta features for it. We weren't afraid of that, and got to digging into the data. And we're using, if you look on sort of the right side of the page when you open it up, it's quite a bit of information on that page. And you pop over from sort of looking at CPU and you change it to looking at heap live size, so the amount of bytes being allocated for your program as it's running. You'll see this big list of stuff. Basically, it's sorted from top to bottom of what's using the most memory. And we looked at that, and this stood out to us as these things shouldn't be taking up that much memory. This is kind of weird. And we'd actually recently, this was very evident because we'd actually recently wrote these files, and it's related to a process to buffer and batch information. So instead of processing data points one at a time, we'll have a 5-second window where we'll collect data points so that we can process them in groups of 20 or 100 or 1,000. And so now we have a place to dig in. We start looking at it, and we're running the code, piece by piece in a console, 1,000.times do, that sort of loop to figure out what is causing my memory problem. And it turns out it's this call to class.new, and it's specifically using a library in Ruby called the dry types library. So there's a whole host of really cool functionality in this dry set of libraries, and this is one we use for kind of structs with superpowers, things that'll let us do static typing and things like that Ruby doesn't give you for free. And so not even a production fix. We actually just said, instead of really figuring out what's wrong, let's just memoize these anonymous classes, because we're only constructing them for maybe a dozen different kinds of objects anyway, this metadata class here, or sorry, this batch item class here. And let's just memoize that. And that way we only do the allocations a certain number of times. Let's see if that helps. And so after we did that, we went back and we looked at the heap live objects. We looked specifically at the comparison view, which is really useful for understanding whether or not the problem that you set out to solve actually got solved. And you can see on the left, we've got heap live objects. It's a little small there, but you can see about 3.5 million objects allocated. On the right, you can see it's 1.99 million objects allocated, much, much better for kind of that same period of time, that same area within the code. So we were able to see we're definitely allocating and holding on to quite a bit less memory in any given point in time. So same thing if you dig into the actual flame graph itself, and you can see on the left, we've kind of got some of the bits of the flame graph highlighted showing those specific methods. Because if you hover over it, you can see it says in there, again, sorry for the size, it says this frame only appears in A. It's only significant enough to appear on the before side, and it's using such an insignificant amount of memory, it's not even appearing on the other side. So this is exactly the result that we wanted to see. Moreover, if we go back to our logs and we think about the original problem we set out to solve, right, is we have these pods that are running out of memory all the time, and we look at that same search, can anybody tell where we implemented the fix? Pretty clear what happened. And we still have this nice long tail, and that's always fun to figure out what's the long tail about. But we did solve the bulk of the problem, which was super nice to see. And so another important result actually in this too is that not only did we solve the out-of-memory error, we actually started to see latency just dropping across the board. So this is looking at the service. This one's Sidekick. We actually split our Sidekick into multiple services in Datadog. If you want to hear all about that, I have a talk from last year about splitting your monolith up into services. But this is going to encompass a lot of data processing work. And all of a sudden, it all got faster, which is also really cool to see. Similarly, this one is our messaging pipeline, so the act of sending messages. We also saw the same result where the latency, we're looking at the P50 latency here, also got quite a bit faster as soon as we did this. So super exciting to see. Not only are we restarting less, using less memory, and restarting less means that our pods aren't rebooting all the time, which just is a bunch of wasted time. It means our system is quite a bit more efficient. So all because we had the profiler to help us figure out where the problem was at. So what we learned, anonymous classes, they're not memory leaks on their own, actually. One of the first things we did was somebody pulled up in a console and activity monitor on their Mac just to look at the Ruby process, and they ran class.new 100,000 times just to see, does memory go up? And it turns out the garbage collector on its own for just a regular plain Ruby class does a great job of cleaning up after itself. However, the dry type library does all kinds of metaprogramming. It's actually a really fun library to dig into the internals if you're interested in a really long afternoon of reading some complicated stuff. It does a lot of metaprogramming where it actually holds on to these class definitions as you make them. And so it probably wasn't meant for anonymous class creation like this. That was sort of our conclusion from having looked into that. And so without the continuous profiler, we honestly would have not had figured that out. So it was a great tool for solving this specific problem. So with that, that's the end of the first example. Our other example of a success, and we have quite a few, I just thought these were particularly interesting, was understanding these excess allocations happening from calls to dup. So dup is similar to clone or copy in some other languages, just how you make a shallow copy of an object in Ruby. So again, looking at the continuous profiler data, and if you look at the CPU side of it, you can see in Ruby profiles, you can see how much time you spend in garbage collection. And it's how memory works in Ruby, and we'll get into that in a minute. But it seemed a little bit high. And so I Googled it. I was like, well, I don't know, is this actually high? I have no idea. And I Googled it, and the internet didn't even seem to know. There's a few threads on Stack Overflow, quite a few very strongly worded posts on Reddit and Twitter talking about where it should be or where it shouldn't be. And I kind of concluded 5 to 7% was pretty normal. So I'm contributing one more data point, I guess, to the world on that one. And we're floating at like 10%. So that seems a little high. So I decided to investigate. So real quick, just for an overview of what that means, how does Ruby garbage collection work? So your program is running, you have this thing called the heap. The heap is just all of your, all the memory that you need for allocating any new objects. And your program's, if you use any kind of library, you're allocating hundreds of thousands, if not millions of objects all the time as you're servicing your requests and doing jobs or whatever your program's doing. And the garbage collector runs, it stops the world, it stops all of your threads from running. And it goes and it marks every object that is in use currently, and it'll traverse the entire object graph to do so. Once it's marked everything, it'll do something called sweep. That's why they call this a mark and sweep garbage collector. It'll sweep away all of the objects that are no longer in use so that it can free up those slots in the heap in order to allocate new objects. And if it works, it will unfreeze the world, and your program is running again, free to allocate more objects and do more work. So this takes time, and like I said, it freezes the execution of your program. So you don't want it to take too much time, and 10% really felt like a lot of time. So what did we want to look at? We wanted to look at the number of object allocations, right? If this is taking so much time to do garbage collection, that probably just means there are a lot of objects out there that it has to go and mark and keep track of and sweep. And so again, I went to the right side of that profiler view to look at that list. And I set the UI to look at the number of object allocations. And we can see at the top, we've got quite a few things. And so this is one thing where it takes a little bit of context, understanding how your program works and what it's doing to really interpret this list. Because the dup, the thing that ended up being the bad thing, it's only the third thing on that list. There's actually other things in front. And that doesn't necessarily mean those other things are bad. In our particular case, the very first one is load for ZSTD serializer. That actually corresponds to reading objects from the cache. And so that's something where naturally there's going to be a lot of object allocations, right? I read a bunch of bytes in, I have to construct all these objects, probably from a call to marshal.load. So you expect a lot of things there. Similarly, the dispatch method on our connection file, that's going to be pulling objects from Mongo, read multi-entries, and another one from cache. So you kind of have to have a little bit of context. But the one that really stuck out there was this dup method. Why is that causing so many allocations? So we just kind of set out and looked for all the dup methods. And this one stuck out in particular. So in one random file related to ingesting event data, so something that we do billions of times a day, there's this method called setUser. And it sets an instance variable to a copy of a user. And so I looked through the Git history on that to see, am I the person to blame for that 6 years ago? Is that something that I forgot that I put in there for some reason? And it was there to fix a logic bug that actually no longer existed. And so I said, all right, let's just try to see what happens if we remove the dup call and we just give it the user outright. And what do you know? The allocations before and after are crazy different here. So before, we were seeing 5.25 million allocations per run of this function, kind of per run, not per run, but when looking at it being called over lots and lots of profiles. And against the new version, we see that it's making 423 allocations, so pretty good size drop. And we look at our CPU time, actually, which was interesting to look at for this method as well, is obviously making these shallow copies of these objects probably takes some time. It turned out to save us quite a bit of time as well, which was super interesting to see. And we go back and we look. Let's look at our garbage collector. Before, we were spending 7 seconds out of every, this is usually every minute, but it says 56 seconds. So 7 seconds out of every 56 seconds, 12% of our time in the garbage collector. And after this change, we're only spending about 6 seconds, which is only about 10% of our time in the garbage collector. So again, doesn't sound like a huge improvement, right? Just like a couple percent here or there. Why does that matter? We'll go back to how we're processing billions of events or running thousands and thousands of processes. This sort of thing really matters in the end. If we're making our entire infrastructure 2% more efficient, that's pretty good for a 3-line PR. So the important result, if we look at the average pod CPU usage, we can see a pretty substantial drop there. Again, you can pretty easily see when this change got deployed. A couple little spikes here and there that I have no idea what they're from, but the overall definitely dropped in terms of the pod CPU usage. And you can see this even more clearly when we looked not just like at all pods, but at the specific deployments that were doing this work that were primarily responsible for running this code. We saw something like a 20% drop in the CPU that it's used, that particular workers needed. And this is especially for the folks that use Kubernetes. This is especially important because as you're putting pods onto different pieces of your infrastructure, it's a bin packing problem. You have a finite number of resources, and you have things that use those resources. So anything you can do to be able to cram more resources onto the same set of infrastructure means you can spin up less infrastructure, so less costly for you overall. So what we learned, code written years ago to patch a logic issue, it turned out to be highly non-performant, something that at the time, without the profiler, we had no idea. So we wrote it, it seemed to work fine, and we moved on with our lives. This was impossible to find without the continuous profiler. I tried, actually, after the fact, knowing it was there, trying some other approaches that I would have tried to find this leak, and I could not, for the life of me, I think I tried every like on your machine gem for Ruby profiling, and I could not get the same result without the continuous profiler, so I thought that was pretty cool. But the real conclusion here is these huge performance gains can be found by investigating profiles. You have to know a little bit about what you're looking for, but when you do know, it's very easy to find these sorts of things. So with that, I'd like to talk about app observability tools and how to find these sort of things, the ways you use these tools, and where profiles can fit in sort of an overall landscape of how to use them. So I gave these the fun name, the 4 horsemen of application observability. And so I always start with logs. Logs are the simple thing that everyone knows how to do. You remember your first programming class where you did a system.out.println or whatever puts to write log messages. It's kind of the first thing that comes to most people's minds when they're thinking about profiling their application, or understanding, rather, how their application's running, figuring out what's happening. All logs are captured, unstructured or structured, both great. Log levels can be very helpful, especially in Datadog. It's easily searchable, and the tools like pattern analysis are extremely helpful for making sense of those log messages, especially when you're spewing out millions of them. After that, you've got metrics, so you can easily capture numerical data in a relatively cost-efficient way. You can use aggregates, so sums, averages, mins, maxes, and slice and dice them using tags, which again can make it very easy to narrow down the scope of your problem. And they're very useful for understanding latency, throughput, number of occurrences, things like that. Both of those require you very much to specifically put those things into your application, right? You're not going to get a lot of value if you don't explicitly write out, log this thing here, or increment this metric there, or record this metric there. Traces, on the other hand, and especially with some of the dynamic instrumentation features in Datadog for some of the runtimes, those allow you for more of a approach that doesn't require you to do as much work. And so it allows you to easily see how your code is running over time. It gives you those lovely graphs where you can see all of the spans when you're calling into your database to get some data, or you're using your cache to put or pull data from there. And you can visually identify anomalies, things like end queries. That's a big one that we're always hunting down at Braze. Is we change some process to work on one user or one data point at a time to work on 100 data points at a time, and all of a sudden we're making 100 calls to the cache. It's really easy to see this stuff from traces, which is great. And the aggregation of traces as well, one of the, maybe not newer at this point, but newer features, allows you to understand how time is spent across many requests, which can also be really useful. Like, how often is this particular span showing up when this particular request is happening? And it connects many services together in one view. So you can, with the power of distributed tracing, you can see across your entire application, especially if your application is composed of microservices, how is it all working? Where is your slowness located, or where your problems may be located? Now, profiles are unique. Profiles allow you to understand what the CPU spends time on. And that sounds really similar to traces. But you have to remember that traces are usually per request, or per job, or per unit of processing that you're doing. And so it's very easy to forget there's stuff that happens outside of that, outside of those requests, or outside of that job processing loop that you may not be aware of, such as garbage collection. It allows you to understand what goes on outside of those defined traces. So actually, one thing that some folks at Braze have been working on recently is actually the algorithm that Sidekick uses to determine what job to run next. And we run a super customized version of the one that's included with Sidekick, and that's not captured in traces. And so it's very nice to be able to see, using the profiler, how much time are we really spending when we're just simply pulling a job from the correct queue. So very, very useful. So why is it important to have all 4 of these tools? So logs have great retention properties, and you can even rehydrate older logs in Datadog to investigate the occurrence of events in the past. They're all going to be there unless you have a problem with log ingestion. They do all exist, which is really nice. Metrics, kind of the same way. They have great retention properties. You could look at trends over long time periods, which we find to be very useful when we're tracking down, this particular request seems to be a little bit slow. Let's look at the last year. Was it a gradual slowness, or did we just miss where one day it hopped from 20 milliseconds to 40 milliseconds? That sort of thing is really easy to identify with metrics. Traces show how your code acts, and so this is a great one for right after you release a new feature and it uses 3 or 4 new jobs, 3 or 4 new endpoints. You can go and dig in. You can see, you have a mental model of how it should work. Is it actually running according to your mental model? Is there something happening there that you were not aware of? Maybe you called into some library code that somebody else in your organization wrote, and it's doing something relatively inefficiently. This is exactly where you'd find that sort of information. But profiles, they show where your processes spend their time and spend their memory regardless of whether it was captured in traces. So very good, again, for finding sort of that space in between the traces, space in between the logs, in between the metrics that may be able to help you find these really tough to catch performance problems. So my last section, things that we're excited about. So we're excited about the idea of monitors on profiles. So I've heard this is something that's either on the docket or in development, being able to do things such as understand, when is part of my application spending 10 or 12% of its time in garbage collection again? Now that I've got that number down, I want to be alerted when that number goes back up. So very excited about the prospect of that. With Ruby specifically, I think some of the other languages actually support this, but with Ruby specifically, we want to investigate mutexes, semaphores, and other types of concurrency controls and concurrency locks. Specifically, we run Sidekick. Sidekick runs many threads. Each of our processes usually use connection pools to every type of thing under the sun, to Redis, Memcached, MongoDB, Postgres. And what if those threads are very frequently waiting on an available connection from the connection pool? That's not really currently very visually well captured anywhere in our observability stack. And so it's one of those things that I've always had in the back of my mind. This might be a problem that we don't know about yet. So very excited for that. We're also excited to profile some of our Golang microservices. So I mentioned we have this monolithic Ruby platform, and it's decorated with all kinds of microservices for very specific tasks. And many of those are written in Golang. And I know that the team that's worked in the profiling code for Golang have done a great job of providing a ton of visibility there. So we're really excited to start digging into some of the performance issues that we've seen here and there pop up in those applications as well. So with that, that's kind of the end of my talk. I'd love to take any questions that anyone has about the continuous profiler and Braze's success with it.
All right, we have 2 mics in the aisles. Welcome up for questions, but let's give a hand to our lovely speaker.
Good.
We have mics in the aisles. Could you, if you are able, or I can also bring a mic to you.
Hey, thanks for the talk.
Yeah.
How would you recommend somebody get started with profiles for the first time? Just some of the screenshots you showed. It's a lot of dense information, a lot of low-level stuff. So, and any recommendations you would have?
Yeah, no, it is. It's very dense, and it's actually fun in that a lot of times I've actually done several talks internally at Braze of like how we've a couple of us have found some of these problems using the profiler, and especially in like a large application, if you're getting started with it for the first time, it's intimidatingly large what's in it. And so I actually have the same advice for actually most of Datadog's products: is build a dummy app that doesn't do much. It does something very simple, and then plug it into these tools. So I actually have a demo Rails application. I'm not exactly sure. It's related to my GitHub somewhere. It might be on my personal one. It's definitely public, that I call Super Counter. And it is a API endpoint, a dashboard endpoint, and a Sidekick job that simply increments a counter. And so something that's like very simple like that, with maybe the moving parts that you're curious about, hooking in all of the tracing code to be able to profile that or view traces on that or whatever, is really a good way to learn it, because it strips away kind of all of this extra stuff that is admittedly very overwhelming, and it really breaks it down into like the fundamentals so you can understand what you're looking at. Yeah, no problem.
Hi. Thank you for that presentation. That was really helpful. Having these profilers run does mean that the Datadog agent will be using more CPU and stuff like that. So my question is that when do you guys decide to turn this on? Like what instance, right? Like using them on all the instances is probably a little wasteful. So what specific instance you choose to turn it on versus not, and how do you manage that?
Yeah, no, that's actually a super good question. So the first time that I turned it on, I think I like exec'd into a single pod directly, turned it on and restarted the process. Not a super scalable way to do this. And it doesn't actually collect that many profiles if you're just looking at like a single running thing. So the way that we do it, so a little bit of background. So we have, like I said, thousands of customers. They have their own users. They all have their own data. So they're split out in a few different ways to spare you the painful details. They're split into their own databases in a few different ways. And those databases sometimes are located on the same MongoDB clusters. And so we think about things by ports. We're talking about connecting to a specific Mongo S port. And so there'll be things like 1, 2, 3, 4, 5. It's an example of that. And that might have 10 customers on that port. And so oftentimes, those ports will also have dedicated resources for message sending or data processing or whatever. And so when we have an idea of a problem that we want to tackle, we usually pick 1 or 2 different ports and 1 or 2 different kinds of worker types. And we just use like Helm charts basically to set environment variables to turn it on for those specific things. That usually gives us dozens to hundreds of machines or pods, I guess rather, where it will be turned on for. And being just sort of Helm configuration, it's relatively quick for us to turn it off and on and fairly developer friendly. So,
Thank you.
Yeah, no problem.
Hi. So I'm curious about how do you determine whether or not it's worth it to go into profiling data? So like you mentioned like you're dealing with billions of users all the time. So like it feels like it's a no-brainer, but like on the other side, the more deeper you go, like in more costs like person hours, Datadog costs, and all that stuff. How do you decide whether or not it's worth it for a particular problem?
Yeah, so usually, so by default, sort of, we have sampling all over the place, right? And it's true with any tool you're going to use. But we always have traces of virtually anything that you're going to find, especially anything that's happening with any real volume. And we'll always have all of our logs. We'll always have all of our metrics. And so that's almost always the first avenue of looking at something, is to look at those first 3 tools that I talked about. Profiles is sort of when you've hit a dead end, when you can't figure out why. For like maybe a specific problem that you've identified in that way. So in our case, we knew the problems were related to memory. And so memory is a particularly tricky one. That one's very hard to determine with logs or metrics or traces. And so that's why we went for the profiler for like that specific problem. Let's say for something that you might see, so you're looking at traces and you have a span representing talking to a database, and all of a sudden the span lengths are getting longer and longer, going into my thing about connection pools and locking and stuff like that. That may be a good time to go into the profiler, because from the spans alone, you may not be able to see it's not actually the database taking that much time. It's actually the process of even getting a valid connection is what's taking that much time. And so I try to think about it as like, could there be anything running in the scope of the problem I'm thinking about where I might get some valuable insight from looking at one of the features in the continuous profiler? So whether that's object allocations, heap life size, CPU time, wall time even can be helpful sometimes.
Gotcha. Thank you.
Yeah, no problem. Any other questions?
We have time for one more.
Is it okay if I just ask you? You said that you turned on all the beta features.
Yes.
Which ones are the ones that were available, and which beta features did you find most useful?
Yeah. Yeah.
I'm going to repeat it for the recording so that folks can. So you're fine. So which features did you turn on for beta was your question? Okay, please.
Yeah, so out of, so the question was which of the beta and alpha features did we turn on, and also which ones did we find the most useful? So the CPU time, I believe, was the one that's like not the beta feature. And so it's useful by itself for sure, right? I could see that garbage collection was taking a long time in terms of CPU time being spent. Also was able to dive into a few other problems not covered in this talk just from that data alone, which was great. I mentioned the process of a worker choosing what job to run next. We could definitely debug that problem that way. The beta features that we used, or alpha features, I'm not sure which one was which, is the allocation count, so the number of object allocations that are happening overall. That one's useful for understanding, especially if you have a problem that is like our DUP problem was lots of small objects being allocated all the time and then just thrown away. That's very useful for finding that type of problem, which isn't going to cause a memory leak because the garbage collector is cleaning those things up. But it will cause the garbage collector to have to spend a very long time running cleaning things up. So that's very useful. I think the alpha feature was the heap live size feature, so understanding not just what objects are being allocated, but what objects continue to persist in memory. So another little deep dive into the garbage collector for the folks interested in this, another thing I could probably talk about for hours. Ruby also marks a concept of age on every object, and so there's actually a multi-step process in the mark and sweep algorithm where Ruby treats new objects, ones that have like a low age count, like how many garbage collections have they survived through, and old, I think it's called old gen, things that have survived for a very long time. And those things are, I think some of that data is actually available. If you have that on, you can see, I can't remember exactly where. You can definitely see it somewhere in the UI. But using the heap live size, the heap live allocations to understand what objects have been allocated by what methods that are still around. And that was very interesting as well, because that was helping us find the memory leak. And then, in fact, that'll be your primary tool for finding memory leaks. Yeah, no problem.
All right, let's give another hand to Zach. Thank you so much.
Yeah, thank you very much.